Yeah, I like the rain. We need as much as we can get in Colorado, huh? All right. So let's get back to that problem. So we need to make the other allylic carbocation in this case. And so remember, it's not about following Markovnikov's rules. It's just about making an allylic carbocation. So we're going to put the proton on this carbon here, which will put the carbocation here. So let's draw that allylic carbocation, which is going to look like this. So here's our carbocation. It's allylic, so it's going to have a resonance form, which is going to look like this. Got the double bond here. Now I have the positive charge up here, and there we go. All right, and now we can get the bromide attacking either of those carbocations. I'm going to delete that resonance curved arrow just so I don't have to reinvent the wheel here or redraw the same thing every time. So the bromide is going to come in as a nucleophile. We're going to produce a chiral center in both of these cases, won't we? So we'll draw the nucleophilic attack here. Oops, I don't know what happened there. Nucleophilic attack there. And we get two more products. So we end up with something that looks like this. There we go. And this is racemic. And we end up with something that looks like this. And this is also racemic. Okay, and the other two products are here. Maybe I could squeeze them all in the same place. You think so? Well, maybe. I don't know. Copy. See if I can squeeze them on here. Come on. So I'll try to squeeze it down here. So let's see. We get. Oops. There we go. So they're every single one of the products. Just delete this here and put it over here. Racemic. So we end up with a total of 4 different compounds that are all racemic mixtures. So if you're sitting there and wondering after doing this, what's the synthetic utility of this? Something where I get a million different products. Well, you know, there's probably some use for this chemistry, and you can control which regioisomer you get. So that's really what we're going to get into in the next section. All right, so let me find my slides here. Oh, I didn't want to do that. Sorry. Oh, sugar. Can you guys still see my screen? You can. Yeah. Good. So let's see here. 3111. So back to chapter 16. We were down here. All right. So we solved both of these. All right. There we go. So now what I want to do is, now that we've solved this problem and this problem, I want to switch gears for a second and talk about thermodynamic versus kinetic control. So I told you that you can actually control the amount of 1,2 adduct and the amount of 1,4 adduct you get. To put it in simple terms, if you do the chemistry at low temperature, you end up getting mostly the 1,2 adduct, and if you do it at a higher temperature, you get mostly the 1,4 adduct. And this is based on, if you're like, well, why would I do it at a higher temperature and get the 1,4? It's based off of the relative stability of the alkene, right? If you look at this alkene, it's mono substituted. So mono, right, is only substituted here. Whereas if you look at this alkene, it's di-substituted. And so it's going to be a more stable compound. So the 1,4 adduct is actually more stable. And that is kind of the crux of why that is the major product when you do the reaction at higher temperature and you have an equilibrium. So it says the formation of the 1,2, we call that the kinetic product, and the 1,4 is the thermodynamic product. Now the first step is a proton transfer to make the allylic carbocation. That's this step right here. All we do is we take the starting material and we make the allylic carbocation. It's the identical step for both. Okay, that is, according to this diagram, it's the rate determining step too, right? Because it has the highest activation energy. But in the second step, the nucleophilic attack, the nucleophile can either attack the carbocation that's drawn here, it can attack this one to make the 1,2, or it can attack this one to make the 1,4. So which one is it? Well, you see that if you form the 1,2, it occurs at a low temperature. Why? Because it's got a much lower activation energy. If you do it at a higher temperature, then there's going to be an equilibrium between, are you going to make some of the 1,2? Yes, but there's going to be an equilibrium where it can go back and forth, and eventually it's going to lie to the side of the one that is more stable, right? So thermodynamics is going to come and be the deciding factor in that case. So as I stated, the 1,4 is more stable because it's disubstituted. So at higher temps, you get thermodynamic. At lower temps, you get the kinetic product. All right, so let's get into the explanation for the kinetic product. And it's based off of what's called the proximity effect, okay? It's nothing more than this. The 1,2 product is going to form faster, okay, because of proximity, right? You add the proton to carbon number 1, and then you have your positive charge right next door on carbon number 2, bang. The bromide comes in and it attacks there, and that's it. So if you're at low temperature, that's what happens. First carbocation, boom, it just comes in and it attacks it, and therefore the 1,2 adduct is going to be the major product at a low temperature. Now, I don't have the explanation of the thermodynamic product, but I already did explain it on this slide here. The idea is this, is if you crank the reaction temperature up high enough, then you're going to have enough energy in the reaction mixture to make either this product, the 1,4 adduct, or the 1,2. Are you going to form some of the 1,2? Yes, but it's going to have enough energy that it could cause this to leave, okay, to regenerate this carbocation, and then it's going to be in resonance with this carbocation. And so there's going to be an equilibrium there, and the equilibrium is always going to lie to the side of the more stable of the two. Really, all you need to memorize as chemistry 3111 students is at low temperature, you're going to have the 1,2 adduct predominating, and at high temperature, it's going to be the 1,4 adduct predominating. That's about it. All right. So with all that in mind, let's take a look at a problem here. This one, it says predict the products for each of the following reactions, and in each case, determine which product is going to predominate. Now, in this case, they gave us a symmetrical diene, so this means we're not going to have a whole holy host of products. We're going to have a couple of products that will be racemic mixtures, but we're only going to end up with 2 products, or 2 racemates in this case. So what are we going to do? We're going to make our allylic carbocation. So in order to do that, we're going to add the proton here, and we're going to end up with an allylic carbocation that looks something like this. So there's our positive charge. And does this have a resonance form? Absolutely it does, right? We could draw a resonance arrow like this and draw this resonance form where I have the positive charge down here. And there we go, something that looks like that. So now our bromide in this case can come in and attack either of these allylic carbocations. So the bromide can attack here. The bromide can attack this one too. I'm not going to put in all the lone pairs just to make things a little faster. So just draw a curved arrow from the negative charge. Technically, you shouldn't do that, but come on. It's the land of the free for 2 more weeks. So there we go. So I end up with this compound as one of my products, and I end up with this compound as one of my products. All right, and of course, this is racemic. This is racemic. If I call this one A and I call this one B, could anybody tell me if we're at 40 degrees Celsius, which one of these is going to predominate? Would it be A or B? Would it be A or B that would predominate in this case? It's going to be B, right? Because B is the 1,4 adduct, right? This reaction is going to be under thermodynamic control, right? Therefore, 1,4 adduct will predominate. So if I count my carbons here, 1, 2, 3, 4, this is the 1,2 adduct, and this is the 1,4 adduct. All right, does that make sense now? Maria, does that make sense now that you've seen me count the carbons? Yes, no, toaster? Okay, cool. Well, let's try one more. Let's try another one. We can redeem ourselves. So Maria, let's start here. If this one's at 0 degrees Celsius, what's going to predominate? Kinetic or thermodynamic? If we're at low temperature. Right, kinetic, due to the proximity effect. So what's going to predominate here? Will it be 1, 2, or 1, 4? Right, so major product, here major will be 1, 2, right? 1, 4 will be minor. So let's see here. If we redraw the HCl molecule here, we want to make an allylic carbocation. So we're going to draw a curved arrow that looks like this. And we're going to draw ourselves a beautiful allylic carbocation that looks a little something like this. Okay, so if we count our carbons, so carbon 1, 2, 3, 4. We start with 1 where the proton is added. So 1, 2, 3, 4. Now we're going to draw the resonance form. I'm not even going to draw the curved arrow. I'm just going to draw it because I'm assuming you know how to do it by now. So we end up with something that looks like this. We have our positive charge over here. So now if we write in the carbons, we have 1, 2, 3, 4, right? The proton, if I highlight this proton in red, right, the proton was added at carbon 1. It's still there, okay? Nothing has changed there. All right, so now I can have the nucleophilic attack by my chloride at carbon 2, like this, or I can have the nucleophilic attack by my chloride at carbon 4, like this, okay? And I'm going to end up with a pair of racemates, aren't I? Again. So I can get this guy, which is the 1,2 adduct, and I can get this one, which is the 1,4. So this is racemic, this is racemic. So this is my 1,2. So this is going to be my major product, right? And this is the 1,4. So this will be my minor product, right? This is the kinetic product. This is the thermodynamic product. So kinetic product is going to be the major product in this case. All righty, does that help a little bit? Everybody just kind of like, yeah, I get it now. Okay, cool. Yeah, there you go. All right, so there's a bunch of reactions called pericyclic reactions that are presented in our textbook. We're only going to look at one kind of pericyclic reaction in this class in Chemistry 3111, and that is what we call a cycloaddition reaction, where you actually form 2 carbon-carbon bonds. So we form a carbon-carbon bond here, and we form another one here. So you can imagine that's a pretty big deal when you can form 2 carbon-carbon bonds at once. And you also notice that this reaction is a concerted reaction. Concerted. If you forgot what the word concerted means, it just means all the curved arrows happen at one time. So there's not a bunch of different steps to the mechanism. Everything happens at the same time. So in the cycloaddition, you probably notice here that we lose 2 pi bonds. So we lose 2 pi bonds. And we end up forming 2 sigma bonds. The ones that are highlighted in blue form 2 sigma bonds. Anyhow, kind of too many hyphens there, but whatever. All right. There's also something called an electrocyclic reaction. We're not going to study this in detail, but you can see that we lose a pi bond and we gain a sigma bond in the electrocyclic reaction. And then there's another class of reaction called a sigmatropic rearrangement where you don't lose or gain. There's no net loss or gain of any kind of bond, whether it's sigma or pi in this case, and we don't cover these. So just to review, there's 3 types of pericyclic reactions. This is the only one that we cover, okay? And what we're going to study is called the Diels-Alder reaction. All right, that's going to be our focus. The other ones, again, are covered in our textbook, but we don't go over them in detail. So what did you notice about those reactions? Well, first of all, I already pointed out that the reaction mechanism is concerted. All the arrows happen at the exact same time. There's no carbocations, there's no carbanions, there's no proton trans. Everything happens at once. It involves a ring. Did you notice that? If you had this 1,3-butadiene and then you combine that with ethylene, you probably noticed that it forms a ring. right? There's like a ring of electrons, you know. The transition state is cyclic, yes. And since there's no carbocation or carbanion, the polarity of solvent doesn't really mean anything in this case, okay? Since there's no charge, there's no delta minus, delta plus, you can kind of run these reactions in a variety of solvents. So that's something that's kind of interesting. So here's a summary of what I just told you. In a cycloaddition, you lose 2 pi bonds, you gain 2 sigmas. In an electrocyclic, you lose 1 pi, gain 1 sigma. And in the sigmatropic rearrangement, there's no net loss or gain of any kind of sigma or pi bonds. But like I told you, we're going to focus on cycloaddition reactions only. And just so you, in case you think like, well, maybe they won't be on any kind of exam. Oh, they're covered on the ACS exam big time, okay? So you want to make sure you know your Diels-Alder chemistry. So let's get into it. The Diels-Alder reaction, like I said, anytime you can make a carbon-carbon bond, you can get famous. And these guys are still famous years after they discovered this reaction. Why? Because you're making carbon-carbon bonds, and you make 2 of them at the same time. We call this a 4+2 cycloaddition because the atoms that are involved in the transition state, right? You have 4 carbons here, and then you have 2 carbons here that are actually part of the transition state. So we call it a 4+2 cycloaddition. There's also 3+2 and 2+2 cycloadditions. There's all kinds of them, but this is the only one I think we look at in detail, I believe, is the 4+2. Also, you notice that the arrows shown here at the bottom, they can be drawn clockwise like this. You can draw them counterclockwise. It doesn't matter. I'll even prove it. If you draw the curved arrows in reverse, am I going? Yeah, I'm going in reverse here. Yeah, you end up with the exact same thing. Okay, so, and if you're like, do you care which way I draw? No, because it doesn't matter. You're going to get the same answer either way. So very cool reaction. Clockwise or counterclockwise, doesn't matter for the mechanism. You form 2 carbon-carbon bonds. Polarity of solvent isn't important. You know, where have you been all my life, Diels-Alder? This is a great chemistry. All right, so if you look at the potential energy diagram of the reaction, you can see that there's an intermediate, you know, where we have this cyclic transition state. Then you end up forming something that's more stable. Well, why would the product be more stable? Hopefully you remember from your Gen Chem 1 days that a sigma bond is more stable than a pi bond, isn't it? Right here we have 1, 2, 3 pi bonds and only 1, 2 sigma bonds. Here we have only 1 pi bond and we have 1, 2, 3, 4, 5 sigma bonds. And so the product of the Diels-Alder is going to be much more stable than the reactants. So let's take a look at that. It says most Diels-Alder reactions are thermodynamically favored at low temperature. Okay, low and moderate temperature. And product stability is going to be the predominant factor there, right? Because this is more stable than the starting materials. All right, good enough. However, get this, and this might boggle your mind, but trust me, you'll understand when I explain it to you. If you crank up the temperature high enough on a Diels-Alder, if you're just, I'm going to crank it up to 250 degrees Celsius, well, then you get what's called the retro Diels-Alder. The reaction actually goes backwards. So whoop, it goes backwards, and you go back to your starting material, and you're like, well, that's kind of crazy. You heat the reaction at moderate temperatures, you get the product, then you turn the temperature way up and it goes backwards. It does, and there's a really good reason for that, and it's based off of everybody's favorite concept, the old delta G, right? Delta G is equal to delta H minus T delta S. And in order for our Diels-Alder reaction to be spontaneous, right, the delta G has to be negative, right? If delta G is positive, then the reaction is not spontaneous and it would go in reverse. So we're going to discuss both of these scenarios, and trust me, you'll get it no sweat once I show you the answer. All right. So the first thing, we're going to look at both terms, the enthalpy term, the delta H, and we're going to take the negative T delta S and we're going to put that all together kind of thing. Like this is just the way our textbook does it. He sandwiches everything together here. That's fine. No problem. I don't have a big problem with that. So first, let's talk about just delta H. Well, if you're breaking a bunch of sigma bonds and you're forming more pi bonds, breaking a bunch of pi bonds and forming more sigma bonds, you're making something that's more stable. And so in that case, it's an exothermic reaction, right? You're releasing more heat. since you're forming more stable bonds. And so our delta H is going to be a negative number. Okay, delta H is a negative number. T is always a positive number. And what about our delta S? Does anybody have a hunch? Is our delta S going to be increasing or decreasing? Will it be a positive or a negative value, the entropy? It's going to be decreasing, isn't it? Thanks, Audrey. Absolutely. 100% correct, right? Why is it going to be decreasing? Because you're taking two molecules and you're making one molecule. So we would put here negative, like this. Where am I here? Plus T delta S. There we go. So, oh, here we go. So delta S should be negative since two molecules combine to form the single product. So we have a negative value here, and then we have a negative for our delta S like that. Okay, cool. So we get that part squared away. So do I have any explanation? There we go. So if we take negative T delta S, and remember that this is a negative number and this is a negative number. So if you take a negative times a negative, what do you get? A positive. So now what we have is a negative and we're adding a positive to it. When are we going to get a negative delta G? We're going to get a negative delta G when this term is small, right? This term is going to have to be small. And how are we going to make this term small? We're going to make it small at a low temperature. However, if you jack up this temperature, if you jack up the T super high, if you're at a high T, that means that this term is going to get bigger than this term, and that's going to convert the delta G to a positive number. So then your reaction is going to be non-spontaneous, and the retro Diels-Alder is going to be favored. Give me a thumbs up if that makes some sense to you. Anybody with me on that, with the whole idea? Okay, cool. All right, just a little bit of Gen Chem 2. Actually, I guess that's Gen Chem 1 and Gen Chem 2 kind of thing here. So if you're wondering, well, what's a good temperature? The ideal temperature for a Diels-Alder is usually between room temperature and 200 degrees Celsius. Past 200 degrees Celsius, you're usually going to get the retro Diels-Alder reaction. All right, well, let's look at this very specific Diels-Alder reaction, and let's give a name to our conjugated system and then our system that only has one pi bond. The conjugated part of the reaction, like here they have 1,3-butadiene, we call that the diene. And the part that only has one pi bond in it, that's participating in the reaction, I should say, we call that the dienophile. So again, to rehash, this is our diene, and this is our dienophile. So diene and dienophile. I'm going to use those terms quite a bit. And if you take a look at this reaction here, this is 1,3-butadiene. We talked about this molecule. This is ethylene. If you crank those up to 200 degrees Celsius, you get cyclohexene, but it's a pretty low yielding reaction. I mean, 20%, that's not very good. That's not super synthetically useful. And so in order to get the Diels-Alder to be a really useful, effective reaction, you've got to have some kind of electron withdrawing group. So we call that an EWG on your dienophile. So I'll put here EWG. Now, I realize that I've spoken to a lot of you this summer. There's some students that are taking this class that are taking other classes right now, and people working a job, and I'm sure just super busy and strung out, and they're just, give me what I need to know, Mr. Dion. I'm going to use that and do my quizzes, and that's great. If you are interested in the concept of FMO theory, the whole idea of the electron withdrawing group, what that does is it has an effect on the molecular orbitals, and that's what improves the reaction yield. I'm not going to go into any detail about that whatsoever, but if it's something that interests you, feel free to read up on it in the textbook. And if you have any questions, of course, you could ask me about that. But again, I'll never ask you a question about that. All right, so if you're wondering, okay, what's an EWG? What's an electron withdrawing group? You just said EWG. You didn't even teach me what that is. Well, you know what? Electron withdrawing groups are going to come up quite a bit throughout the rest of this course, okay? At least for the next, I'd say, 3-4 weeks. So let's take a look here. We have our diene, and now we have a dienophile. And if you're like, well, why is this electron withdrawing? Well, the carbonyl here is an electron withdrawing group, right? You have a dipole going in this direction, so that is considered to be an electron withdrawing group. In fact, anything that's got a carbonyl attached directly to the double bond, be it a ketone, an ester, carboxylic acid, even a nitrile, right? Because a nitrile, if you draw the Lewis structure of a nitrile, it's got a triple bond, so it's electron withdrawing. Any of these groups that are highlighted in red, they're all considered to be EWGs. And so what do? They increase the yield, okay? They make the reaction very useful. We went from something like a 20% yield to a 100% yield. I just threw my hands up in the air when I said 100, even though nobody can see me. I mean, that's a very high yielding reaction. That's as good as you're going to do. So before we get into some specific examples here, you could practice drawing your curved arrows on your Diels-Alder every time. You know, just give it the old college try here. So there's the reaction arrows drawn, or the mechanism arrows drawn in a clockwise fashion. But anyhow, I digress. Before we get into some specific reactions, I need to cover a few more kind of nuances about the Diels-Alder with you. So the next thing is that a Diels-Alder is stereospecific. If you want the Sparks Notes version of that, if you're starting out with a cis dienophile, you end up with two groups that are cis to each other, okay? If you're starting out with a trans dienophile, you get two groups that are trans to each other. That's it. It's stereospecific, okay? If it's E, right, if they're opposite, you end up with anti-addition, or they're trans to each other. And if you're starting out with something that's Z or Zusammen or cis, okay, then the two groups are going to be on the same side of the molecule. Nothing more than that. You can also use an alkyne as a dienophile, right? It's got 2 pi bonds. You only need one of them, but you can still use it. And so you could draw the same old set of curved arrows like this, but now you end up with a 1,4-cyclohexadiene intermediate. So just so you're aware of this molecule here, I shouldn't say intermediate, I should have said derivative. So 1, 2, 3, 4. So you'd call this molecule 1,4-cyclo, I'm running out of space here, hexadiene. Okay, so 1,4-cyclohexadiene. All right, so with all that in mind, it says predict the products for each of the following reactions. We got a whole holy host of dienes and dienophiles here. I just want to check one thing here. Oh, I think we can't do this yet, okay? I'm going to write here later because we haven't covered all the rules yet. Sorry, I put this slide too early. Okay, I have to show you a couple more concepts. So we looked at the fact that a diene can exist in the S-cis and the S-trans conformation. If you remember, this one was more stable, right? Well, it turns out that Diels-Alder reactions can only occur when the diene is in the S-cis conformation. So it's got to be S-cis in order for a Diels-Alder to occur. And check this out. If you have a diene that's locked in a trans conformation like this, so this one's locked in a trans conformation, it won't react at all. Okay, you get nothing happening. But check out the one on the bottom. If you have a diene that's locked in an S-cis conformation, like cyclopentadiene, this molecule here, that will react like stink. I mean, that will react at room temperature probably. I mean, it just reacts like crazy. And you end up forming this bicyclic species here. Now notice, since the two X groups are trans to each other, one of them is going to be pointing up and one of them is going to be pointing down. And if you're like, oh man, I'm not sure about drawing a bicyclo compound, I haven't seen those since Organic 1, don't worry, we're going to take a look at a few examples and I'll try to help you on that. So going back to the idea of cyclopentadiene, like I said, if you have cyclopentadiene in a bottle, like if you have a bottle, right, Audrey, let's say you go to the store, you know, where is it? Target probably. And you buy a bottle and it says cyclopentadiene on it, well, you better keep it at low temperature, because if you keep it at room temperature, it's going to do this. It's going to form this compound here, dicyclopentadiene. And so if you're wondering, well, how do you make this compound then if it's so reactive? Well, think about it. If you heat it up enough, so if you subject it to high heat, it's going to do the retro Diels-Alder, and that will give you the starting material back. If that makes any sense to you at all, I still expect you to be able to draw the curved arrows for this because it's just a regular Diels-Alder, but it's kind of the concept is kind of an interesting one here, right? Anyhow, I'm getting overly excited about this. So let's try this question before we go back to that one that's got a bunch of, you know, crazy reactions in it. It says rank the following dienes in terms of reactivity in the Diels-Alder reaction. So anybody want to suggest, if I call this one A, I'll call this one B, and I'll call this one C. We'll go most reactive. We'll go least reactive. Can anybody suggest, there's one of these that's by far the most reactive. Can anybody suggest which one it would be based on what I showed you? Yeah, thanks, Sydney. Absolutely. B is the winner by a long shot, okay? The other two don't even come close. Can I ask you a different question? Is there anyone here that won't react? Would just be so unreactive, it's just, no, not going to happen? No, not C. Okay, so let's hold on, let's review. Okay, the reason B is so reactive is because the diene is locked in the S-cis conformation. Right? This is locked in S-cis, right? Goes like this, right? It's locked in that way, okay? But in A, you see this is a fused ring, so this is locked in S-trans. Okay, so that's going to be completely unreactive. That can't react in a Diels-Alder. It's impossible. This one looks like it's trans, doesn't it? But we know that there's free rotation around a sigma bond. So you could have something that looks like this. Son of a gun, did I really put my pi bond in the wrong spot, didn't I? So you'd have something that would look like this. All right, so that would be the S-cis conformation if you rotated that. So there's going to be some steric hindrance because of these two methyl groups or whatever, but it's still going to be possible. So B would be, or sorry, C would be intermediate, something like that. Can I show an example of C reacting? Sure, yeah, C could react. So let's say you took C, right, and you had it like this, okay? And then you just combined it with, something like this. Well, you're going to be able to form a sigma bond here, a sigma bond here, and then you form a pi bond like that. And so that would give you a 6-membered ring, right? That's going to have a pi bond here. You still have these two methyl groups. You have these two methyl groups here, and then you would have your carbonyl up here like that. Does that make sense? Something like that. Okay, cool. And if you're like, I don't follow Tiana and Mr. Dion, don't worry. We're going to come back and we're going to do a whole bunch of2examples. But I still have to explain a couple more concepts. So I forgot how many concepts there were. Let me teach you 1-2 more rules, and then I think we'll call it a day. And then on, what's today? On Friday, we could come back and we could just practice. So let me teach you 2 more things, okay? So just bear with me. 2 more concepts, and then we'll call it a day, because there's a lot of concepts here. So the first thing I'm going to teach you is the endo rule, and the last thing we'll look at is regioselectivity, and then we'll be done, okay? Well, let's do that. So where are my students? There we go. Okay. So when you form a bicyclic system, okay, and right, we learned how to name bicyclo compounds way back in Organic 1. When you make a bicyclic system, there's 2 possibilities, right? If you have a cis dienophile like this, you could have the 2 groups pointing down, and we call that the endo product, or you could have both of them pointing up, and we call that the exo product. So you can have endo or exo. And you can even draw the protons in here if that helps you. Right, you could draw this one down here, this one, maybe I'll draw it like this, okay? Okay, so we have endo and exo. All right, so if you're wondering, like, what's the definition? Well, exo, it means it's anti to the bigger bridge, and exo is syn to the larger bridge. Usually my students just remember that the endo one is the pointing down. It's on the side of the bigger bridge, okay? Which is totally fine. And it turns out that the endo product is the major product. And if you're thinking, well, that one looks more sterically hindered to me than the exo, you're right, it is, okay? So it says here, the electron withdrawing groups attached to dienophiles tend to occupy the endo position. The endo product is oftentimes the only thing that we get. So we call this literally the endo rule, okay, is that we usually form the endo product. And why is that? Well, there's a long explanation, but the short version is what's shown here on this slide. It's that during the transition state where the dienophile reacts with the diene, it says the endo transition state. So I'm reading right off the slide. The endo transition state benefits from a favorable interaction between the electron withdrawing groups and the developing pi bond. So between these electron withdrawing groups and the pi bond that's being formed, there's a favorable interaction. Now, if you're like, well, that's not a very deep explanation, you're right, okay? That is as deep as we go in this class. We just say there's some kind of interaction there. There's some kind of electronic effect that makes this transition state much more stable than if it was exo. So when it's exo, these two pi bonds are too far apart from the pi bond that's forming, and so we don't have that favorable interaction. And so that's why the endo is the major product and the exo product is usually not even formed. Now, if you look at the reaction coordinate diagram, the whole idea is this, is nothing more than this, man. It's just the endo activation energy is a lot lower. That's all. Why is it lower? Because during the transition state, you have a favorable interaction between the pi bond that's being formed and the pi bonds on the electron withdrawing groups. There you go. That's your explanation. That's as deep as we need to go in chemistry 3111. So there's one more thing I want to present to you before we call it a day, and that is the idea of regioselectivity. You can see my slides are a little messed up in terms of their order. So I want to cover this one more topic with you, the topic of regioselectivity. Let's say you have a diene that's symmetrical and then a dienophile that's asymmetrical. You don't have to worry about regioselectivity in that case, right? If you look at both of these reactions that are on this slide, there's no regioselectivity to consider. You just draw your curved arrows, you draw your product, you walk away, wipe your hands, and you're done, okay? But what if we had an asymmetrical dienophile and an asymmetrical diene? Well, how are they going to react? Let's say you had something like that. Are they going to react in the orientation that they're shown here? Are they going to react like that? Or is the dienophile, I'll just draw it, like this, okay? This one would give you this product, but if it reacted in this orientation, it's going to give you this product. So which way is it going to react? That's regioselectivity, okay? So it's a great question, and we actually can answer that question with, nothing is easy in organic chemistry, but I'll say relative ease. In order to answer the question, though, you've got to be rock solid on your resonance forms, okay? You're going to be rock solid on your resonance forms. So let's take a look at the diene. If you draw the resonance form of the diene, we have an allylic lone pair. Hopefully you remember the patterns of resonance. We have an allylic lone pair, and so we can draw a resonance form of the diene where we show the negative charge on this carbon up at the top. Now, you could take the dienophile and you can draw a resonance form where you show a positive charge on this carbon at the bottom. So it stands to reason, based on those partial charges, if I redraw this resonance structure that has a negative charge on this carbon, okay, it's going to react with the dienophile in this orientation, like this. So I'll just draw it upside down compared to how it's drawn here, because then you're going to have the positive and negative interacting with each other, right? That's how it's going to align itself. So you see it shown here. Now, usually the way that we do it is the way that's shown here. We just put partial positives and partial negatives, but you can draw explicit resonance structures the way that I've shown, and just say to yourself, well, look, the positive and the negative, they're going to be attracted to each other. Those are the two ends that are going to come next to each other. And so that will be my regioselectivity. That's it. That's all. That's the answer of regioselectivity. Nothing more than that. So based on all that information, next class, we're going to cover this question where we look at regioselectivity. I want to cover this question, which doesn't really deal with regioselectivity, but in this one, we have to draw some bicyclic products. There's one that's even a tricyclic product. I want to go over this one here where we actually where we draw a dienophile and a diene that you would use to make a Diels-Alder product. And that's the last slide. I want to go back to the slide where there was a question that we didn't answer. Where was it? This one here. I want to try and predict all of the products of these Diels-Alder reactions. So I think that that's enough information for today. And so what we're going to do, again, when we come back, is we're going to solve question 16.13. This is on Friday afternoon. We're going to solve, where was it? Where was the next one? It was 16.17. We're going to solve 16.18, 16.42, and the last one we're going to do is this one here, 16.43. So we're going to do all of these questions, every single one of them in class on Friday. And so we're a little bit ahead. So remember, this is the last slide, okay? So yes, our book does go all the way up to 16.13, I think. We don't cover those sections at all. I'll leave that as an FYI. Again, they won't be on the quiz. They won't be covered on an ACS exam. I've never seen them asked on any study materials or PCAT or anything like that. So if you're interested in a standardized exam in the future, do not stress about it.